Hi everyone. In this particular video, we're going to go to molecular dipoles. And as I mentioned earlier, this is based on bond dipoles. So we need to have an understanding of bond dipoles for us to be able to go ahead and predict molecular dipoles. And molecular dipole, as the name suggests, is the dipole moment for an entire molecule. And it is the vector composite of bond dipoles. So the bond dipoles contribute to the molecular dipoles. And so that's why we need to understand how to draw bond dipoles first. So what I've done is I've selected a few examples here, and every example for a specific reason, because I want to show you some of these things. Okay, so let's go ahead and get started. And again, as I said, the molecular dipole is a composite of bond dipoles. So we need to draw or predict bond dipoles first and use that to come up with the molecular dipole. So we'll start with water molecule first. Okay, let's see what does the molecular dipole for a water molecule looks like. And the bond dipole itself, remember that it is based on electronegativity. So for water molecule, when we look at it, we have hydrogen connected to oxygen. So for this OH bond, the hydrogen-oxygen bond, oxygen is more electronegative. So the bond dipole for this bond is going to point towards oxygen, because hydrogen here is del positive and the oxygen is del negative for this particular bond. The same is true for the other oxygen-hydrogen bond. So bond dipole is going to point towards the oxygen atom from the positive end to the negative end, from the partial positive element to, or from the partial positive atom to the partial negative atom. Okay, and then additionally for oxygen, we have two lone pairs. So lone pair is basically electrons, electron density. So for the two lone pairs, the bond dipole, not a bond dipole because there isn't a bond as such, but the dipole is going to point towards the electron density, towards the lone pair. And for the other lone pair, it's going to be the same. Okay, so those are all the bond dipoles for water molecule. Now, how do we come up with molecular dipole based on these bond dipoles? So what we have to do is now we have to basically start adding these in a very physical sense, okay, and come up with the molecular dipole. So, and these are based on vector additions, but we don't have to go into the math a lot. All you have to remember, sort of, or you have to identify is that when you have two dipoles pointing up, slanting, pointing up, okay, they're at angles pointing up, the composite of these two dipoles, okay, the composite of these two dipoles, only these two is going to be in the middle, pointing straight up. Okay, that's the composite. And again, notice how the positive end is near the positive end for the two bond dipoles, and the negative end points towards the oxygen. Similarly, for the lone pairs, again, the dipole is pointing at angles, but it's pointing out. And again, so the vector composite for these two dipoles is going to be pointing up. Okay. Now I can go into more details, but I'm trying to avoid that right now. So basically the component of this dipole which we have to factor in, or which we have to include, is the one that is pointing up. For dipoles that are pointing in or pointing out at an angle, the composite dipole is going to be the middle. So we basically looked at these two bonds and we looked at those two lone pairs. And so now what you notice is that the two composite dipoles are actually pointing up. Okay, they're both pointing in, pointing up. So the overall molecular dipole, so this is a composite dipole. That's what I've drawn in red. Okay, that's a composite dipole. So the overall molecular dipole now is going to be the vector sum of these two. And since these two are pointing in the same direction, the overall molecular dipole is also going to point in the same direction. And this molecular dipole has contributions from the two composite dipoles. They basically add up in some sense to give you this molecular dipole. So that would be the molecular dipole for water molecule. Let's look at chloroform. We again did bond dipoles on chloroform. So let's look at chloroform next. There's no dipole for a carbon-hydrogen bond. For the carbon-chlorine bonds, the dipole is going to point down in all of these cases. Okay, so that's the direction of the bond dipole. And again, this is a tetrahedral carbon. Okay, so let's look at a tetrahedral carbon here so that we are able to visualize this. Okay, so for that chloroform molecule, you can assume that this is the hydrogen atom, the carbon atom is here, and these three are the chlorine atoms. Okay, so that's the tetrahedral. So now this carbon hydrogen bond has no dipole. All the carbon chlorine bonds, they have a dipole, and the composite of the dipoles for all three of these carbon chlorine bonds, since they are all sort of slanting down, they're at an angle pointing down, the composite for all of those dipoles, the one that actually matters, is in the middle, like that. It is pointing down. That's where the dipole shows up. Okay, so that's the one that's going to add up, the dipole that actually adds up. So the composite dipole in this particular case is going to be pointing down, away from that or across from that carbon hydrogen bond. Okay, so exactly down like that. That's going to be the composite dipole. And since there are no other dipoles that we have to consider here, the overall molecular dipole for this molecule is also going to be pointing down. Okay, that will be the direction of the molecular dipole. Now, I've drawn another representation of the same molecule to actually put across a point and realize that this, sorry, my bad. Okay, I have an error here. These are not hydrogens. These are chlorines. These are chlorines, and it's basically chloroform drawn flipped now. Okay, so what would happen in this case? So now in this case, again, there's no dipole here for the carbon chlorine bonds. The dipole is pointing up towards the chlorine atoms. So now we have the same molecule, but now it is flipped over like this, and there is dipole along all of these carbon chlorine bonds. So the composite dipole for all of them is going to be pointing up in the middle like that. Okay, so the composite dipole is going to be here. That's the composite dipole. So the way I've used here is I'm using red for the composite dipole. The green is the molecular dipole. So this molecule and that molecule are the same, but they're drawn differently. In this particular case, the chlorines are pointing down. In that particular representation, chlorines are pointing up. And so in this particular case, although it's the same molecule, the dipole is going to point up. Okay, that is what I wanted to convey here, that there is nothing like for chloroform, the dipole is pointing down. Okay, the molecular dipole should point down. The molecular dipole, the direction in which points is a result of the way the molecule is drawn. So keep that in mind. Okay, there is no hard and fast rule that it has to be drawn a certain way. You could orient it whichever way, and then you're deducing or you're arriving at the molecular dipole based on your three-dimensional representation. Let's go to this molecule here, carbon tetrachloride. So carbon with 4 chlorine atoms. Now in this particular case, notice how there's going to be a dipole pointing up. And for each of these carbon chlorine bonds, there should be a dipole pointing along the bonds. And like we saw in the case of chloroform, the composite dipole for the three at the bottom. Okay, so for these three, the composite dipole is going to point down. Okay, that's the composite dipole for those three. Now, it turns out the magnitude, that means the quantity of this composite dipole, which is from these three. Okay, so 1, 2, and 3. Those three dipoles are contributing to this composite dipole. So it turns out the magnitude of this composite dipole, okay, when you do the math, if you were to do the math actually, the magnitude of this composite dipole equals the magnitude of this one carbon chlorine bond. Or the other way to think about it is each of these carbon chlorine bonds contributes only 1/3 to this composite dipole. Okay, so 1/3, 1/3, 1/3, that's 1, and this is one carbon chlorine bond, and they actually are pointing in opposite directions. Notice how this composite dipole is pointing down, the other composite dipole is pointing up. So they actually cancel each other. And so the net dipole for this is 0. So there is no dipole moment essentially, okay? 0, so there is no dipole. And now we're talking about molecular dipole. This molecule has bond dipoles in it, but there is no molecular dipole because the bond dipoles cancel each other out. Important to remember or important to realize, okay? I've chosen another molecule here, which is sort of derived from these structures, but now has 2 bromines and 2 chlorines. So let's try to work out the molecular dipole for this molecule. So carbon bromine bond, molecular dipole pointing up, carbon bromine bond, molecular dipole pointing in down, carbon chlorine, molecular dipole pointing that way, carbon chlorine, molecular dipole pointing there. So those would, sorry, not molecular dipoles, bond dipoles, my bad. Bond dipoles for each of these is going to be pointing along these carbon halogen bonds. Now, we have 2 carbon bromine bonds, so we can add these up to come up with a composite. That composite, since it's pointing in that direction, it's pointing down, should be in the middle, pointing up like that. Okay, and then we have 2 carbon chlorine bonds, and so we can add these up to come up with a composite, and that composite should be in the middle here. Okay, that composite is going to be in the middle. Now, if you notice, we have 2 composite dipoles, one for the carbon bromine set, the other for the carbon chlorine set, and similar to this scenario here, they are pointing in opposite directions, okay? They are pointing in opposite directions. One's pointing up like that, the other one's pointing down. So they're pointing in opposite direction. So does that mean that the dipole is going to cancel out, like in this scenario? In this particular case, the answer is no. Why wouldn't they? Because this composite is based on a carbon bromine bond, and the other composite is based on a carbon chlorine bond. And so this is where the electronegativity of the elements comes into play. Chlorine is more electronegative compared to bromine. That means the magnitude of this dipole, okay, or the magnitude of this dipole here is going to be larger or bigger. So in terms of numerical value, quantity wise, okay, the magnitude of this dipole, the carbon chlorine dipole, is going to be bigger than the carbon bromine dipole. And so because of that, what happens is this carbon bromine composite dipole can partially offset the carbon chlorine dipole. So that means it's going to cancel it out, but not completely. It's only going to partially cancel it out. And what that means is for this molecule, we are going to have a net molecular dipole in the direction of the chlorine atoms, okay? Pointing towards the chlorine atoms, because this is a bigger dipole. compared to the carbon-bromine dipole. So I hope that is clear. Okay, so it does not cancel out every time. It depends on the electronegativities of the contributing atoms. Let's look at a very different structure here. Again, we can draw bond dipoles for the carbon chlorines here. So we should have a dipole pointing up, and then we should have a dipole pointing down. And we are drawing it for the two bonds here because everything else, this is a bond line structure, okay? Everything else is carbons and hydrogen. So I would actually encourage you to draw out all the carbons and hydrogens here and make sure that there is nothing else which would have a dipole, a contributing dipole. So what we notice is we have two carbon chlorine bonds which have dipoles to them. And we do not have to draw a composite dipole here, but notice how these two dipoles, they are pointing in opposite directions and they are the same elements, carbon chlorine, which means this again is going to have a zero net dipole, or the molecular dipole for that molecule is going to be zero. So this is how we basically draw molecular dipoles based on bond dipoles, and it is for a particular structure that's given to you in a particular orientation, as you saw. Okay, so that's going to be this video, and what we're going to see in the next video is how we can use this information, or at least part of this. This is going to be one of the contributing factors in understanding intermolecular forces. Okay, so that is a video on molecular dipoles.